Section 4.2, mean value theorem. In this section, we will look at the Rolle's theorem and mean value theorem, which are the application of the derivative. For Rolle's theorem, let function f be continuous on the closed interval ab and differentiable on an open interval ab with the function at a equals function at b. There is at least one point c on an open interval ab such that the f prime at c or the derivative of the function at point c equals 0. In summary, we can say the assumptions for the Rolle's theorem are: number one, the function f is continuous on a closed interval AB. That means the graph is connected from point A to point B, or is only one single curve from point A to point B. Number two, f is differentiable on an open interval AB. That means the graph is smooth from point A to point B, or within point A and point B. Assumption number three, the function value at A equals function value at B, or the two endpoints give the same function value. And the conclusion of this Rolle theorem is the derivative at the point C equals 0, where C is some point in between point A and point B, or we call C is the interior point. Let's look at the example. The function f is x times x minus 1 to the power second from point A0 to point B1. So in this case, let's make a list. A is 0, B is 1. And the function, if we expand it all out, we're going to get x to the third minus 2, x squared, plus x, which is another form of the polynomial. But the assumption number one, the function is continuous because this is the polynomial which is continuous everywhere. So we can say this function is also continuous on the closed interval 0, 1. Number two, f is differentiable because we can find the f prime as 3x to the second minus 4x plus 1, which is another form of polynomial. So we can say the function f is differentiable on an open interval 0, 1. And then assumption number three, the function value at point A equals the function value at point B. Let's find out these two numbers. F is 0, which is 0, multiplied by 0 minus 1 squared, which is 0. And the function at 1 is 1 times 1 minus 1 squared, or 0. So these two numbers are the same. Checked. Then, by the assumption of the Rolle's theorem, there is the point C on an open interval 0, 1, somewhere between 0 and 1, such that the f prime at C, or the slope of the tangent line at the point C, equals 0. And we're going to find the point C, since the Rolle's theorem does apply, with the conclusion that f prime at C equals 0. As a function f prime is 3x squared minus 4x plus 1, so we replace x with the value c to get 3c squared minus 4c plus 1 equals 0, and then we solve for c. This expression can be factored completely as 3c minus 1 multiplied by c minus 1 equals 0. We get two values of the c, as c equals 1 over 3 or c equals 1. 1 over 3 is on an open interval 0, 1, but c equals 1 is not on an open interval 0, 1 because 1 is already one of the endpoint. So we just keep c equals 1 over 3. And the function value at 1 over 3 is 1 over 3 multiplied by 1 over 3 minus 1 to the second power, or 4 over 27, which is about 0.18 something, 0.148, sorry. And then with the um s- with this conclusion, we can say that the graph of the x times x minus 1 to the power second from point 0 to the point 1 is a smooth graph. That means the function is continuous and differentiable. And there is the point C in between 0 and 1. Since we found c equals 1 over 3, so this order pair is the order pair 1 over 3, 4 over 27 that has the tangent line with the slope 0, or has a horizontal slope occurs at the point c equals 1 over 3, which is the point in between 0 and 1 by the mean value theorem. Next, look at the second example. The function f of x equals 1 minus x to the power 2 thirds, on a closed interval, a equals -1 and b equals 1. Is the function continuous on the closed interval ab? The answer is yes, because this is a power function with the degree 2 over 3. So we can rewrite it as 1 minus the cube root of x squared. The cube root, there's no restriction. So any number you can use as the input, or the domain is a set of all real numbers. So we can say the function is continuous on the closed interval -1 comma 1. Next, is the function differentiable? Let's see. F prime in this case is -2 over 3 times x to the power -1/3, or -2 over 3 times the cube root of the x. When you have the rational function form like this, the denominator cannot be 0. Therefore, x cannot be 0. That means the derivative is not defined at x equals 0. So f prime is not defined, or we cannot find the derivative at x equals 0, which is the point on an open interval -1, 1. Therefore, the second assumption is not met, and then we can say the Rolle theorem doesn't apply for this case. As you see the graph from -1 to +1, the graph is connected. Yes, it's continuous, but it has a sharp turn at the point 0. That means the slope on the left side is positive infinity, but the right hand side is negative infinity. So the slope doesn't exist, or the derivative is not defined at the point 0. So not differentiable at x equals 0. So then the Rolle's theorem doesn't apply.